So in this video I am going to show you how to implement this pixel processor reconfigurable circuit on as a dynamically reconfigurable implementation. Okay, so what I'm going to do is just to follow along the tutorials of the tutorial number 7, okay, and the first part, the test project with the pixel process. This circuit is right here, right? Here is the interface, as you remember, the input FIFO, the output FIFO, and here these 4 LUTs, they make up the reconfigurable partition, okay? And we allow, I guess, for a parameter f, and depending on the parameter, right, if f is 1, so right here we have a different variation in the partition, and if f is 2, which is a parameter, we have a different variation in the partition. A variation is just different values, you know, loaded onto the LUTs. Okay, so the main problem with this kind of system is the following: that it is not just the peripheral that you are showing, it is also the fact that your peripheral now includes, of course, the PS, right? Let me show you in a moment. Let me see if I can AXI for full and peripheral. Well, first of all, we have to rearrange the code structure in order to expose the reconfigurable partition. That's the idea, okay? And the way we did it is just by simple rearranging of the code such that, you know, this is your code, right? This whole thing is your peripheral. From this block here, that is your peripheral. However, everything underneath, of course, is, you know, the associated files. But as you can see here, we have one file, right? And then underneath that, all of those files, you know, corresponds to this top file. Okay, so that is the top file of your reconfigurable partition. Okay, I usually use an _RP there to indicate that it is a reconfigurable partition. Okay, so this would be, I guess, easy if we only had to deal with this top block, right, the peripheral itself. But no, right, in this kind of system, the static region, right, includes, I guess, a portion of the AXI for full peripheral, in this case the pixel processor peripheral, plus, in this case, the PS, for example, and some extra circuitry that I will show you in a moment. Okay, so that is the problem with this kind of systems. So now we have to include the PS and the extra circuitry. And the problem is that we do not have a VHDL description for the PS. Okay, unfortunately, no, we don't have it. Okay, the format is a different format, right? It's a proprietary format from Xilinx. So what are we supposed to do? Well, we have to do some tricks here. Let me see. So you remember in your peripheral, right? You have your peripheral, and you also have, of course, what? The PS, absolutely. And if you remember, I can show you here, just a moment, your circuit also included something called a system reset and also the AXI interface. So these 3 components, right? For these 3, we do not have a VHDL description. Okay, and give it a little while. Yeah, they are right here, right? This block, right? This is the PS and this is the AXI interconnection system. So these 3 blocks now we have to somehow managed to include them in the static region. Okay. So, well, one way to do that is, I think, through the use of what we call checkpoints in Silence. It's like a snapshot of a design at any stage. It could be after synthesis, after implementation. It's kind of a netlist file, right? So, and I think in Silence they are, at least in Vivado, the extension is .dcp. Okay. So we're gonna make use of that. So the idea here is to, let me show you what is the process here to follow to implement this kind of systems. Okay. There are some moments. Well, somehow we have to get the static. We have to get the description of the static region. Okay. This used to be easy, right? This used to be only VHD files, but in this case, no. In this case, it would be a DCP file. Okay. So then, in order to do this, this is a process that you have to follow. The first thing is the following. Given the peripheral, well, the first thing is just design, I guess, design a, let's call it quote-unquote normal AXI for full peripheral, or a normal hardware software system for the AXI for full peripheral. Okay, so that is the first procedure, and that is something that you already know, right? It's just a click here, click there. I think you have a lot of examples in the tutorial number 4, for example. Okay, so this part is easy because you already know how to do it. What are you supposed to do here? Well, also launch SDK. We will use this system to test, our design, our partial reconfigurable design. Okay, even though that system in itself, it is not a partial reconfigurable design. So then, what are we supposed to do next? Oh well, we have to actually be able to get the static region. Okay, to get the static region, well, I guess the way you can do it is the following: design a static hardware software system for the AXI for full peripheral. And this part is tricky because how are we supposed to do that, right? Well, if you remember, if it is static, right, that would mean that your circuit, your static region should not include this file and or anything underneath it. So it should not include the Pixel ESD and the files underneath. Okay. So how are we going to do that? I will show you in a moment. It is essentially the same as this one, but we're going to remove manually the VHDL files. Okay. And you will notice, of course, that this circuit is not possible to implement because there is no there is a black box, right? Okay, it is empty. But we will, the important part is that we will get the synthesize design, static region. That's a file that is is a DCP file. That is the really important part of the second part, by the way, because that is what we really need. Okay. Then the next part is going to be just relatively easy. 3 is just create, remember, the file structure for the partial reconfiguration flow, right? So what is the file structure? Well, if you already have this, all you have to do is to generate this file structure. I think I have an example here, right here. You create this file structure. Now notice something, right? Just a moment, sorry. Here we go. Notice something. The file structure, right? If you remember on HDL and top, this is where the static region VHDL files are, right? In this case, it is empty, right? Because we do not have a VHDL description for the static region of the image. Well, and of course, well, also to be fair, also just to mention on the XDC, as you can see, it is also empty because we are not using the IOs of the PL. Okay, there is no reason to have that XDC for the IO constraints. Okay, so that's the first thing you gotta notice. Okay, you create this file structure. Not only that, that's something else I need to tell you, and it is mentioned, by the way, in the tutorial. Anyway, here is the thing. Just a moment. If you remember on Synth Static, right, on this folder right here, on this folder, what is going to happen? Well, what's going to happen is the following. We will copy, or we will place the DCP that we got from the synthesis of the static hardware software system. So before, if you remember, this folder usually would be populated automatically, right? Because the VHDL files of the static region are synthesized, and of course the results are placed here. Let me say, usually this is populated automatically by synthesizing the VHDL description. Okay, but of course, here, right, we do not, as I mentioned again, we don't have a VHDL description. So in this case, of course, we will just have to synthesize this static region on our own. Okay, I believe this might be, I guess, I think the most complicated part of this procedure. Okay, and after that, you know, I mean, there are a few things that you need to do too, by the way, but I mean, that's not really you know, very, very important to show you in the general process. And number 4 is just follow the tutorial, which, to be fair, the steps will be similar to those of unit number 6. If you're sorry, of tutorial number 6. To be fair, okay, that's what I wanted to tell you. Okay, so that's the process. Okay, that's the procedure that we gotta follow. So let's now go over it, and it is explained right here in this tutorial course. So what happens? Well, for this tutorial, what I have is this zip file that you can download. It includes 3 folders. Essentially, the first folder is the peripheral, right? The peripheral files, all the files that you need to implement the peripheral. The second folder are the same peripheral files minus the reconfigurable partition. Okay, so let me just show you. Once you download and unzip this file, here, as you can see, that's the peripheral, right? The normal peripheral that you know of. And in static, it is the peripheral, but without, right, the Pixful RP, and of course any other files underneath that Pixful RP. Okay. The only difference, of course, is that notice here how I use I changed the name a little bit to static. Why did I do that? Well, only because they have to have a different name. Okay, because otherwise, if you run this in the IP repository, right, you cannot have peripherals with the same name. Okay, so that's the only change I made. Okay, so in your case, if you're working on your example, you have to do something like that. Define a VHDL project only for your peripheral, right? Run it, simulate it properly, and then define a bunch of files that only work for the static region, okay, of your peripheral, of course, of your peripheral, okay, and change the name here. I use static, you can use stat, whatever you think, but something that that you can recognize. And by the way, that is all I did. I changed the name here, and of course, if I change the name here, you gotta be careful, right? Also change the name here in the entity, and also change the name right here. So everything is just static. Okay. What else did I change the name? Also here, right? I included that right here and here. Okay. So, like I said, it is like a recipe, and it can be a bit, annoying. I mean, like too many steps, but this is the best way I have found for this to work. Okay. So, what is the first thing? Like I said, the first step is to actually design a normal hardware system. Right? Here, of course, you just refer to tutorial number 4. Right? That's pretty straightforward. And by the way, of course, to save time, I have already done that. And here is the system, right? And here is your circuit. Okay? And I already implemented the whole thing, and also I launched the SDK project, right? And here is, and I will explain to you that in a little bit, the piece of software that will implement, the partial reconfiguration testing. Okay, so I have that ready because we will use this project, right, to test. Okay, so now we close it, and this gonna close it too. And now we're gonna move on to our next part, which is actually getting this famous DCP. Okay, we have to get another file too, but to be fair, this is the most important part. Okay, if you cannot get that, I mean, yeah, there is nothing we can do, to be fair. Okay, so how do we do that? Well, according to the tutorial, right, you have to create an embedded system. You can use whatever name you like, right, for the pixel processor minus the reconfigurable partition. Okay, and we're only gonna synthesize. Okay, so how do we do that? Well, we go here. Here, this is the folder of my first hardware software system that I already worked on, by the way. And now I am gonna create another folder that will be my Pixful DRSys. And I'm going to create a new project there. You see? Just give it a little bit. Sometimes it takes a little while more than we expect. Pixel DRC static. So now we have to do the following: Pixel DRC static. Okay. And you select the board you want to work with. Doesn't matter, right? I mean, it could be the Zygo or the Zygo Z10. I mean, whichever one works for you. We do the Zygo Z10. And here we go. So what are we going to do? We are going to create a peripheral without the reconfigurable partition, and the name is right here, my Pixel static. That's the one that I chose, of course. It has to be different because I already have in the repository, my Pixel, of course. You gotta have both there. So I'm gonna go here, create and package a new IP, a Pixel static, right? And is full to is slave, same thing, right? And you know this procedure, right? What I'm going to do now, I'm going to go here, I'm going to grab all these files, I'm going to copy, and I'm going to paste it on the repository folder of the static. Here we go. I'm going to, just a moment, I think you got to let it finish first please. Don't rush. Don't try to, by the way, to outsmart this software. It has many bugs sometimes. Okay, so now I'm ready to copy. And of course, I have to replace the first two. There you go. Okay, so now what do we do next? We have to add the source files, right? And they are where? In repository, static right here, HDL, and everyone minus these two, of course. And by default, for some reason, in 2019.1, the files will also be copied into a source folder inside the IP repository. I mean, you might or you might not. It's up to you. I prefer not to make it more difficult, so just keep it in the HDL folder. And there you go. Okay. So now this is completed. Let's give it a little bit until the structure updates. Look at this. I'm gonna do this, and look at this. This part here, this question mark, means that this part is missing, of course, as I expected. Right. So now what I'm going to do, just in case run synthesis, you will get a warning, of course, that this component is not available there, but that's okay. Okay. So to be fair, I think in this procedure, this second step is the most complicated one, unfortunately. Okay. And by the way, why are we going through so much trouble? Because remember, in the tutorial number 6, this was much simpler. Well, you have to go through this trouble because this is the only way that I know consistently that you can implement a PR project, right? That includes the PL plus the PS, right? And that can be reconfigured via software. Okay. So if you really want to get that, I mean, yeah, you gotta follow this procedure. Okay. So let's give it a little bit of time. Sometimes it takes longer than expected. Okay. Of course, don't run implementation. Let's cancel it here. And remember, when you gotta be careful here, okay? This is a special, is a very special Vivado project in which you have to indicate the packager, all the changes you made. And one of the changes you made is not just replacing the names of these files. It's also you included more files, right? So you would think that the software would be smart enough to detect that you included more files. Well, no, it doesn't. You have to do it, indicate this manually. So you go here, you see the part that is not checked, and you just say merge. And then review and package, and then repackage it. And there you go. Now you go back to the original one, create a new block, and now you're going to create your block with this AXI peripheral without the reconfigurable partition. And then you're going to synthesize, and once you finish that portion, that's when you can get the finally the static region description, right, of this system you want to build. Okay, so let me just static, nothing is changing, you just I'm getting ahead of myself, there you go. And here just in case validate, but you know, if you're letting the hardware do everything on its own, this shouldn't be an issue. This is I think a small bug. It has with the delays for the memory. You don't need to worry about that. You go to sources again, right, and create. Oh, here's the important part, and this is why you have to be very careful here. This is the really tricky part. By the way, this depends on the version of the software. Unfortunately, when Vivado synthesizes a circuit, there are many options. One way to do it is by it creates a synthesized version for every IP in the system. The problem is, if you do that, you will not get the general synthesized DCP file. What do I mean by that? That you will not get the DCP, what is it? Sorry, the DCP description for this whole circuit, minus the reconfigurable partition. You will get a bunch of different circuits, like a DCP for this, a DCP for this, a DCP for this, and a DCP for this. This is not what you want. You want a DCP for everything, right? For everything, of course, minus the RP. Because of that, you gotta follow this tutorial, to the letter. Okay. Older versions had a different way of doing it. Here, of course, you have to select synthesis options, and then you say out of context per IP. Usually, that was not selected by default in older versions, but now it is. You have to select the one that say global, okay? So that only one netlist, right, is generated for the static design, because we only want one netlist. So how do we do that? We go here, and then we do right here, generate output products, and then you see how out of context per IP is clicked. So you do global, and then you say you can do generate if you like, but just do apply and cancel, right? Or close this. Once you apply it, how do you know that it applied? Well, you double check here. It's already global, right? So now, what you want to do is just, as you know, just generate the HDL wrapper. Okay? So you see, this particular, portion of the design is the most complicated one. There are way too many steps that you have to follow, very carefully. Okay, and now, what do you do now? Well, you do synthesis, because when we do the synthesis, it is when we're gonna know, right? We're gonna get the synthesized netlist for the static region, which is what we really want. Okay, and how? Let me explain to you what are you gonna get. You have to get this is the more precious file, the synthesized file for the embedded system. The embedded system, remember, that only has the static region. It is in this file, in this folder. It's called Design1 Wrapper DCP. Okay, it's a netlist. Actually, you can double click on it, and another project will open showing you the design. Okay. By default, I am not, by the way, 100% sure about this, but I never tried. I used to also extract these two XDCs. Okay, I discovered, recently, that apparently you only need this one here Okay, that's the constraints of the PS. Okay, so let me just, is it ready? No, did I set this inside? No, it's not, it's still working, sorry. So in this step, of course, right, what do we do again? We get, let me just make it clear, we get the synthesized static region, right, and then also we will get the constraints of the PS, okay, which is an XDC file. You have to get those files, okay? And that is all. To do that, of course, you have to finish, the synthesis, okay? But once you do that, I will tell you what to do, because in this particular project, of course, I already have a my dynamic folder, right? Remember, with the folder bitstreams, checkpoint, implement with all the variations that you want. So this is the thing that you have to create manually on your own for your own design. Also, the folder synthesis too, remember, right? And of course, the folder sources, right? With HDL, like I said, remember all those files, right? I hope by now you are supposed to know, how to populate those folders, right? It's right here, it's explained. You have to copy these files here, right? Each one with a different variation for the reconfigurable partition. Everything else, right? Everything else is just a bunch of empty folders, okay? What about the names? I think I already explained that. Well, the name for the reconfigurable module, right, or for a variation of a reconfigurable partition is up to you. You decide what name to give it. But if you choose a name, of course, in the TCL file, here you see you have the name of the reconfigurable partition, and here you have the name of your variation, okay? Pixful_1 and Pixful_2. That is your choice. I mean, you have to, if you change it here, you have to change it to the name of the folder, okay? And what else? Well, when you go here, implement, of course, it's just the same name, but you have to attach config, okay? So we're almost ready. What we need to do now is the following. We need to place the static region DCP, the description of the static region, the synthesized portion of the static region. We have to place it in this folder. We just copy and paste. And then also we have to place the XCC, the constraint file for the PS, in sources, right here. Okay, and that is all. And once you are that, once you do that, you are ready. So now you are ready for the PL flow, right? The tutorial. Okay, so the synthesis is still running, by the way. It takes longer than expected, but now once it finishes, we have to do step number 3, which is just copy particular files, right? We create a file structure, of course, and what is it? Like I said, sorry, the folder XCC is empty, but you have to place the constraints, the XCC of the PS. Okay, so this step and also this step are important steps. Okay, this is let's call it step 1 right here, and this one here, that would be step 2. Okay, so now we are ready. Let's see. Usually it takes, of course, it's taking longer than expected, especially when I have the recording here. But let's give it a little bit of time, and then we can complete. Okay. Okay, so now it completed, right? And all you have to do now, we don't need this project anymore, by the way. What we do need though is to do, copy the proper files, and they are of course located in a specific directories, right? This file and this file. As I said before, I used to include this file too, but I realized that lately that actually you don't need this anymore. So let me go over that. So you're gonna go here. You go into remember the static one, and you go to this is runs synthesis 1, and then you go here. That is the static file description. So netlist, you wanna copy, and you are going to place it onto synthesis, of course. Static. There you go. That's the first step that you need to take. The second step is actually going into, I think, sources, and then sources. I think it's IP, and then it's PS, of course. Which file is it? No, processing system 70. There you go. Design 1 processing 70. So you copy that file too, but of course you copy it now where? Into actually sources, right? Because those are actual sources. Okay. So now finally you are ready to start the partial reconfiguration process. Okay. Like I said, this is the most difficult thing that you have to do, but I think it is very powerful, by the way. So now you have everything you need, right? And well, now you have to just, run the partial reconfiguration process. Okay. Like I said, you add the DCP files, like I said. Right? We already did that, by the way. And we will run the design tickle file, right? Which is the one that where we actually define the reconfigurable modules here, right? All you have to do, by the way, here is just select the name for your reconfigurable partition that should match the VHDL name, and here the name of your variations, and that's all. Everything else, this 1, 2, 3, 4 lines, 5 lines are the same. If you want more, you copy more of this. Copy more, okay? And that's it to refer. This one, I mean, it matters a little bit when you are trying to do the design complete, which we are not gonna do here. But I think to refer up to this point, that's all that you need to do. This one you can do if you want to, a configuration for every variation. The config module 1 variant 1, which is for this. Config module 1 variant 2, which is for this. So you do one of them for every variation. Okay. So, but that is all we're gonna do. And of course, notice here, we're only gonna run synthesis for the reconfigurable modules. We are not running synthesis for the top because we already did that manually. Okay. What about these three? Well, we're not doing these three because we're gonna do this, step by step, command by command. Okay. So now let's just follow the tutorial, right? You will notice that this is much easier now. So now you have to go into the tickle shell. Okay. Now, of course, the problem is that you have to navigate to the folder. Okay. You have to navigate to the folder. Well, I think it's in D in my case. Is it in D? Yes. You navigate. I know, of course, where my folder is at. And where do I go next? My D. No, that's not it. Sorry. It's actually CD. There, and then here I'm gonna go into my dynamic pixel. And then here, now I have the tickle file. What do I have to do? I have to actually, according to this, run the Tcl script, which will actually, what will I be doing at this point? What I will be doing is executing what I will be doing is synthesizing every one, let me show you, of these variations, 1 and 2, and the results of synthesis will be placed right here in this folder, right here and right here. So that's all that we're going to do here, and that's all that Tcl command is doing. Okay, so let's just give it a little bit until it completes. It's going to take a little while. Okay, so what do you do after that? Well, it's just, you have to do a bunch of commands, believe me. A lot of commands. Okay, I think in another tutorial, I will show you how to actually use the design complete, but it is not so straightforward. You still need to do at least up to this point. Okay, you still need to do up to this point to actually be able to run everything fully automated. Okay, but today, to explain how things work, I'm gonna go do everything manually as well, so you know what's really going on. Okay, so now let's see what we're gonna do. Is it ready? No, it's not ready. So one thing that I want to mention is the following. There is one particular piece of information that is very, very important, which is it's not here. Is it here? No. Probably not. No. This is the has to be right here. There is probably. It has to be on top of Pixel RP. I have this. Yeah. So, okay, here we go. That's what I call, this is the, remember what I call the, what is it? The reconfigurable partition. And the label I chose is JI. Okay. So now, something important to remember is the reconfigurable partition, and we call that instantiation name, JI. The problem is that if you remember in this system, right, JI, sorry, is right here, right, but JI has a long path to go to get all the way to the top. So there is a path here that we don't know yet. So this will be like this, path. Okay, because you will need, by the way, this the entire path. That will be the actual instantiation name of your RP. Okay, and that's the first thing we're going to do. So this is ready now. Apparently everything went okay, and of course it skipped the implementation, verification, and bitstream, of course. And now I'm going to do what? We're going to continue with the tutorial, and the tutorial says, well, let's start the Vivado GUI. Right? So let it open, and the first thing we're going to do is actually we're going to synthesis. We're going to open this design. Remember the static region. That is our first job here. Okay. So now I'm gonna do that. But by doing this, open checkpoint. Remember. There you go. Let's give it a little bit of time. The first thing we gotta figure out is, by the way, is this name, because you have to know that name in order to proceed with the tutorial. Look at it, because the next steps, right, require you to know this name to load the reconfigurable module right into the black box of the static region. You can see it's here too. We need the same, right? And here, you know, almost everywhere you need that thing. So when this opens, of course, you will see there is a critical warning, right? It is saying that this black box cell, the pixel reconfigurable partition, is not available, right? And well, of course, it is not available. And but here, this is the actual path. That is what I want. Okay. So I copy that, by the way. So that will be, this is what I want. Okay. And you save it just in case for your reference, of course. Okay. So please remember this. Okay, that you gotta save this. Okay. I think there are other ways to get it, I think, but as far as I know, I think that's the only way I know how to get it. It will tell you, of course, I mean, what's going on. But if you go here, right, the path, you go here, and then you go the export static, of course, use 0, whatever that is, down, GIP, I think it's like this. You see, here, notice your pixel RP is actually empty. I mean, this blackened thing is actually empty. And notice here, right, if you click on that, you can actually here, you know, it will show you the entire path too. That's another way to do it, by the way. Or even here, you can just copy and paste this part too. Okay, either way, that's how you can get that very important, you know, information. Okay, so what are we supposed to do now? Well, according to the tutorial, and by the way, you already know this because this is very similar to tutorial number 6. The only difference is that you are using this very long path instead of just a simple layer. That's the only difference, by the way. Well, the first thing is to load, you know, a particular reconfigurable module into the partition, and you have to do this, right? But of course, you have to do it with the proper path. So that's what we're gonna do. We're gonna load the pixel 1. It doesn't matter. You could have started with 2, but you have to load a particular DCP or description or synthesized description of the reconfigurable partition right onto this block, and you will see once you do that, this thing will populate. So let's do that, okay? So I already have, of course, the command. Let me see if this works. There you go. I have the entire command. There you go. So notice how now this thing is populated. It's not blackened anymore. What else do I have to do? Now you have to set this I guess block as partially reconfigurable. It's like you apply a property to it, right? So it recognizes that as a partially reconfigurable. And then, just in case, and you know, this might not be really necessary, just save, you know, this new, let's say, hardware, right, kind of different hardware into a checkpoint. Okay. So now, let's continue, right? So now here is this is the as you already know, this is now another difficult part, unfortunately. Okay, so if you manage to pass this part, I mean, you're almost done, by the way. So now what do? Well, easy, right? We go here, we select this, and we're gonna select the region the reconfigurable partition is going to occupy. And before that, let me just maximize a little bit here so I know what's going on. Just in a moment here. There you go. So I go here, of course, and floor planning drop P block. I kind of already know what's more or less what this thing likes or not. Depends. I think if I do it like this, I think it's fine. Let me see. Maybe not. It might not like it right away. And here, how do you know if it's enough or not? First of all, you gotta use the area, right, for the largest variation, right? That's very important. I know I think if you go to properties, no, statistics, I think, oh yeah, 71%. Maybe it's too small, too little, but we'll see. I think you should never pass of 80, I think, in my experience, okay? That gives you an estimate, by the way. So now what do? You are not done yet, by the way. It would be so easy if that was all you have to do. No. You have to actually run what we call a DRC. And to check, remember, for the partial reconfiguration warnings, okay? If you get a bad warning, I mean, essentially it won't work at all, I guarantee you. I guarantee you. Forget about the pin planning, by the way, it doesn't matter, because we have not yet, loaded the PS IO constraints, right? So we don't need to worry about that. Oh, and apparently I was very lucky. I did not get any, what is it? Any weird warnings, okay? Remember that in the tutorial number 6, I go over some of these warnings, right? And how to get, deal with them. But be very careful, okay? You should be very careful. Let me see if I have it just in case. Because, just to let you know, because you might forget, and this thing actually can be a headache if you don't do it the right way. If you go here, you see, I mentioned some of the particular, of the very, very, very nasty warnings, especially this, HDPR 26. It will tell you that the P block has a left or right edge that is improper. Believe me, if you leave it like that, when you implement, it is not going to work at all, okay? That's very important. If you see this, be very careful, just change it. Change the size or the shape of the partition. HDPR8 is not so bad. It's, if, depending on your application, okay? In the case of the Pixel processor, remember, we don't have, of course, flip-flops inside the PR, so we don't have to worry about this. Sorry, inside the RP. I don't know why I call it PR. So this is supposed to be RP, by the way, I'm sorry. So in other cases, I mean, you might be able to actually control the PR on your own, so you don't need to pay attention to this, okay? But this one, of course, absolutely, be very careful about this, okay? You have to usually go here and delete and then start over and run the DRC again to see if it's working or not. Well, apparently this thing actually worked really well. So what do we do now? The next step, of course, is to we're gonna save these constraints, because these are actual constraints. Right. There you go. So if you, at any point in your design, are got to this point, you are essentially almost done. Right here, you see F-plan ACC. So those are the constraints. It is telling you where your block will be located at. You see, it is telling you everything. Okay, that file is, by the way, very, very, very important. By the way, okay. I think in the next example that I will show, I think is the DCT. You will see how you only need to complete, sorry, up to this point, right? And then, I mean, you have to do a few, modifications, and then you can just run the design complete tickle and then just create the bit streams right away in one single go, okay? But in all of your designs, you have to get up to this point, okay? So also, I always recommend this. If, for example, you I don't know, at one particular point in your project, you were able to generate this file, save this file, okay? Believe me, you don't want to be dealing with this thing over and over. If you got it at once, just save it, okay? So you don't have to do it again. All right, so I think this is very good, and now we are at a really good point. What happens if you save it and now what happens if you hack this file already? So you don't have to do any of this, and instead what you do is actually the following. Instead of write XDC, you just do read XDC, right? You don't have to do anything else, okay? And everything will be loaded automatically. Okay? But that is if you I mean, you still have to do the whole process at least once per project, of course. Okay? Okay. So now let's continue with the tutorial, of course. What's the next step? The next step is to, let me see, we need to read in the constraints of the PS, right? This file here, because we already have them. Okay? Again, let me repeat myself. If you had this constraint before from a different, version of your project, you can just do here read, right? R-E-A-D, XDC. So let me do this part here. So I am going to create that, or sorry, copy and paste and execute that. There you go. Forget about the warnings. I mean, in my experience, this thing works very well. And now what else? Now we're actually, I can say that I am at a point where I am ready to, implement my first configuration, my first variation. I have to do these steps and then, of course, save the checkpoint. Okay. So that is my first variation. And what do? Optimize design. As you will see, what we will be doing from now on is very repetitive. And this is why in this example I will show you how to do it in a more automated way. Okay? Place design. And then, well, assuming this works, of course, sometimes some weird things might happen, you never know. It's going to take a little bit of time. You see, now you can see more or less what's going on. And then you have to do the important step, which is route your design. We hope that this works fine, and then so now what else is there to see? Well, we are ready to do the second configuration, right? And you can do more if you like to, of course. It's up to you. Okay. This might take, of course, longer than we expect. Let's give it a little bit of time. Okay, it completed, and then now we're gonna do this. Right? Save that checkpoint. Okay. Well, I'm gonna skip the report, by the way, just to save time. And here's the important part. Now we have, I would say, our first configuration fully routed. So what do we do now? We have to now get the second configuration. But to get the second configuration, we have to remove, right, the RP from this configuration. Look, this is the configuration with the RP is here, right? You can see it here in this box. So I want to remove that. So there's a particular command that you can use to remove that. There. Okay. I mean, we remove because what? Because I mean, before we removed, of course, we saved, that checkpoint right here, right there, right? We save it right there. Okay. What else do we have to do? Well, you also have to, and this is an important step, by the way, because if you want a next configuration, it's not enough to remove the partition. You also have to make sure that the IOs of the PR are actually locked in place, so they are always there. You run this command, okay? And now you see how you have it now, and now finally you can actually, like I said, you can actually finally have what we call a truly static only checkpoint, okay, at this stage. This is actually the real static checkpoint, okay? By the way, I already explained this in the tutorial number 6, but I'm explaining this again anyway, okay? So we're gonna save it, and that's our truly static design, okay? If for some reason something happens to you, your Vivado crashes, right? You can always start from this block, right? You can open it and then you can what? You can read this checkpoint again. You can read things, right, to fill up the next configuration, and then you do everything again. So this one is extremely important, by the way. Okay, please do not just think that you can open this, right, and then just read this checkpoint. Because if you do, I mean, the two configurations might have a slightly different I/O constraints on the RP. So be very careful. Okay, this procedure requires you to lock the placement, all the place and route. Okay, so that the two variations are actually compatible. Okay, so everything actually is from here. So I think in one of your labs you have to do like 5 different variations. You know, I would just always open this file, right, and then just reading a new checkpoint, and then, you know, optimizing the synthesize and everything else, right? So now, of course, we have to open this guy here with, I guess, with open checkpoint. But I guess we don't need to open here because after all, it's already open, right? So we're gonna go here. We're gonna just again read in the next checkpoint, but that will be the checkpoint for the second variation, right? We're gonna fill in, right, this block with the second variation, or the second reconfigurable module. So here, let me see. As you can see, this is still, you know, black table. It's empty, of course. So we're gonna fill it up with the second one. There you go. And once you do that, what's next? Well, you just implement, right? Optimize design, and then place, and then route. Okay. Let's give it a little bit of time. Okay. So what happened there? What did I run? Oh, optimize. So I'm gonna do now place design. There you go. And after that, you have to do the route design. And once you do that, you are actually almost done, because all you have to do after that is to generate the bit streams, which is what we like. So now that I did route, now I do, sorry, I did place, now I do route. Okay. This part is the part that takes the longest, depending on the size of the project, of course. All right. And if that you know, is successful, you will just you can just you know, save that as a checkpoint. Okay, and we're gonna use these checkpoints right here, right, to generate the proper bit stream. Okay, did it work? Yeah, apparently it did. Alright, so I'm gonna just write checkpoint for it. All right. So you will see, of course, you are noticing how in this folder, right, everything is getting populated, right? Even here in the implementation, there is one variation here, and here there is a second variation. That's what we need, of course. And now, what is the next step according to the tutorial? We just generate the bitstream. So we're going to close this particular project, and then now we're on to generating the bitstreams. What do we do first? Remember, as I said, never, by the way, forget this step, because you might have made a mistake. Always verify that the two variations are compatible, of course. Right? This is why we had here, what is it? The lockdown, because sometimes the students forget about this and then they try to verify and it doesn't work, of course. That's very common, very common. So let me just verify that both are compatible. And if they are compatible, well, that's good, right? Which means that now we are ready to actually you know, complete this. We're almost ready. It's going to take a little bit of time, but yeah. We're almost ready. Just let me check something just in case I'm missing something. Okay. Just in case. it's okay. Let's do it in our own way. Right. So luckily this thing, it should tell you here they are compatible. These two designs are compatible. If they are not, you might get the bitstream, but it's not gonna work, I guarantee you. Okay. So what do we do? What do we do now? Remember, we load the first checkpoint. There you go. So I'm gonna open the Vivado project, of course. All right. Okay, so with this Vivado project open for you, you have to actually generate a bitstream. All you have to do is to do this, write bitstream. There you go. Okay, and when you do that, it will generate actually two bitstreams. Okay, the whole and the partial. Okay. All right. And here we will face a little problem, and this is a problem, unfortunately. Okay, let me see. It's a bitstream generation. So as you know, so far, of course, we have dealt with the following: .bit files. They are good for a JTAG-based reconfiguration, but for a software-based reconfiguration, it doesn't work. And there's a reason for that. There are ways around it, but it's not very consistent. So instead, you have to use bin files. Essentially, what is a bin file? It's a bit file without a header. Okay, that's unfortunately a proprietary format of silence. Okay, so we have to do that. Generate the bin file, the bin versions of it, bin. So we completed that, and as you can see here, if you go to the folder, you will see here those two. So that should be enough, but no, it is not, unfortunately. Yeah. So let me see. So how do you generate bit files? There is a command here. It is telling you how to do it. It's this command right here. Okay. So we're gonna go here. We're gonna do that. Let's give it a little bit of time. Take it longer than expected. Okay, once it completes, it's actually really cool. So here you see the bin file, and then in a moment it will show you the other bin file, the partial too. So now, well, and here is something that you might not like, by the way. Unfortunately, these files here, the bin file actually, these bin files cannot be used, to program the PL using the pickup. Well, actually, they can be used, to be fair. Let me explain very briefly, because this step I think is gonna get lost soon. Okay. Normal bin files, are how do I explain this in a better way? Okay, let me see. Okay, in software, the ARM processor, of course, uses little endian to represent the bytes. So every 32-bit word in a, let's say, bin file has to be byte swapped. Okay, and you can do this via software. We can just stop here, and via software we can actually do this modification, right? Or we can generate the bin files with the bytes swapped. We're going to do this method now, but you can also do it via software, by the way. So this is just to let you know. So you have to run this weird command here. Has particular, modifiers. Okay. Well, now finally you are done with this first configuration. We will use this thing, the U, partial U. That's the one that we need to use, okay, and to download onto our SD card. Okay. Next, what do we do next? Well, now the next version, then the next variation. We close the project and then we open the second checkpoint. Let's give it a little bit of time. It will open, by the way, a different here. You have to always locate here, by the way. Okay, and here, of course, you have to generate the bit streams. Okay. Let's give it a little bit of time for that to complete. It's going to take a little bit of time. Okay, so now it completed, right? So now we generate the bin files. And by the way, I think, to refer, I don't think you need this step to refer, because we are only interested in the actual, byte swap bin file. But, just for the sake of consistency, we want to do the same. Okay. So you do that, and then we're gonna have to do this part. So, but as you notice, some of these steps are very repetitive, of course. And the idea is that, at one point we're going to actually do it in a more efficient way, of course. But I am just showing you the steps, right? So, we know what's happening, every step of the way. Okay. So let's just give it a little bit of time. It takes a little bit longer again than expected. And here we are. And now we do the real byte swapped bin file. Okay, so now that's it. I think that is it. To refer, what do we do after that? Oh, if you want, you can always generate a blank bitstream. This is just following these commands. I mean, to save time, let's just stop there. So let me do close project. Okay. Let's see, because after all, even the software that I have doesn't use this black box to refer, so there is no need to do it right now. So you can test this using the normal JTAG interface, right? You can program this manually, but I think you are not really interested in that. I mean, you are to some extent, but it's not really the important part. This is the important part, doing with the software. So now, what are we going to do? Well, we are going to close this thing. Oops, no. Close this project. And we are going to open, remember, the project that had the SDK, PX, the complete project, right? So I'm going to launch SDK as well. But before we do that, we have to, of course, our two bin files, right? Just a moment here. We have to place them into our SD card. You see, this one and this one, those two files. So I'm going to insert my SD card adapter in my computer. Some of you, by the way, might need a special adapter to the USB. Okay, and here is my SD card. I'm going to copy these files, and well, just to be clear, they asked me to name it as Pix1P and Pix2P. Actually, I think they are actually here, because I did it for a different project, of course. But if I were to use them, it's not going to work, of course, because it is not associated with what I want now. So Pix, I think that would be 2P, right? Because that's the second configuration, and that would be, let me see, Pix1P. That's the first configuration. There you go. Okay. So now we are going to, let me see, this thing already finished. So we're going to actually launch SDK, right? And I am going to now, insert the SD card right into my Zygo Z710 board, right? You gotta do carefully, please. Be very careful. Read if you can, but don't destroy it. Because if you destroy it, there is no way around it. So now I already inserted that, and now I am ready to, execute the software, and hopefully it will work, right? Assuming there are no weird errors happening at this point, right? Which, of course, it is entirely possible that they happen. So let me now, of course, read this in. Essentially, I will show you. Okay. So, of course, first you need to program the entire big string. Okay. Just a moment here, sorry. Okay, testing. First, you have to load the full big string. Then load the partial big strings via software if you like, and you can test, of course. Okay, so that's the procedure I'm going to follow here. And apparently the way it works is the following. First, I'm going to try to load the partial bit string number 2, actually, this one here, and test, and then I load, first I load the full bit string number 2, to be fair, yeah. This one I test it, just in case, and then I load the partial bit string number 1 and test it. And then I load the partial bit string number 2 and test again. If I get these numbers, that means that it has been reconfigured, successfully. Okay, so that's what I'm going to do. And here is the software application. So I already created that, by the way. I think the only thing you need to be careful is generating the linker script, of course. Right, everything should be in the DDR, and you should have at least, what is it? No. 700 kilobytes for your heap and 4 kilobytes for your stack. Also, make sure to always, in the BSP, because we are using the SD card, in your BSP, make sure that you are using the SIL FFS library with the use string function enabled. You have to replace a 0 here by 1 that is here. Okay. By the way, those steps are already specified in in tutorial number 5, I think. I already explained that, okay? So now, very, very briefly, because I think we're running out of time now, how does it work? Well, the most important thing, don't touch, most of it. You might need to touch, I guess, this library, a different one. But all of this, just keep it as it is, okay? This one, of course, you might need to actually, use your own function if you want, okay? But this one, don't touch it, this particular file, because that is the function, sorry, that loads the bit stream to the pickup. And how does it work? Easy. First, like I said, it's gonna test the pixel. Sorry, the pixel processor. How does it test? It's right here. It's a simple function that writes 4 words and it retrieves 4 words. Right? Very, very simple. You know it already. So here it will just test out. Let's say this example. Right? It will, assuming that you loaded the second configuration, it will input this and you should get this. Then what happens? Then we're going to actually load the bit streams. Okay. And let me just show you. I think we didn't notice, but look at it. Look, each of them had actually 115 kilobytes only, as opposed to 2 megas that are the full bit stream. So that might be very useful, by the way. Okay, so just in case here, we separate memory for those 2 bit streams, right? And then we use, this thing you don't touch. I mean, this thing you might touch, of course. You might need more bits or fewer, right? So here, no. So here we separate memory, and then everything else leave it as it is, and then we load, right, the bit streams using this command, load SD to memory. Okay, well, we load a binary file, and you have here the name. Okay, and then everything else you keep it. And here, of course, when you are ready to perform DPR, partial reconfiguration, all you have to do is to use this command, load bitstream to pickup, and you use what? A pointer to whatever bitstream you want to load. So here we're loading actually first the first variation, and then we're testing again, and then we load the second variation, right, in that B, the second variation, and test again, and that's all. That is all that you have to do. Okay, that is all that you actually need to do. Okay, so we're going to test this out, and hopefully it will work. One important thing that I want to mention is the following: how do we load the full bitstream? Okay, well, do it from Vivado, of course, right? Do not do it from SDK, because it has a full bitstream. You see, that is not associated with partial reconfiguration. Remember, what is the bitstream of the SDK project? Well, it is one that was created in this project, right? That had nothing to do with partial reconfiguration. Okay, so you need to actually load manually here. So we're gonna go here, open Hardware Manager, and we're gonna load automatically. So connect. Like I said, in Windows 10, somehow in my computer, this thing takes a long time. I think honestly it's a bug, because I have a Windows 8 computer and this SDK actually runs very fast. Okay, let's give it a little bit of time for it to complete. Okay. Okay, here now we are ready to program the device. Of course, this first step, programming the full bitstream, has to be manual. Forget about this thing, by the way, because this is the bitstream that was created, right, in this project. We don't care about this at all. We don't need that. So we have to manually go to the folder, to the particular folder where we have our bitstream, right here. And we use, I guess, you can use, by the way, either of them, by the way. I'm going to use bit just in case. And now I want to program it, okay? After that, of course, you do everything through SDK, okay? So it's taking longer than expected. Let's give it a little bit of time, okay? Okay, it's finally completed. So we're going to just, since we already programmed the board, remember, we can just quickly open the port, right, that we want to. And now let's run, of course, to see if there were no errors. Let's take a look. Yeah. Now let's take a look at what happened here. Let's double check, okay? So the first thing, of course, is when we did not do any partial reconfiguration at all. So, just a moment. Let's give it a little bit of time, sorry. Here we go. So the first one is when we did not do any partial reconfiguration at all. So we're supposed to get the second case, right? 0C1758DDF, and that one is 9FF8DC2. So this is good. So the third one is working, but the third one is working. So, but so far there has not been any reconfiguration. Now there is reconfiguration. You see, loading the first bit string to memory. This is the number of bytes that it takes, and then we load the second bit to memory, of course, and then what do we do then? We actually are doing the DPR, partial reconfiguration, okay? And we test. Here we perform the first reconfiguration, by the way, and here we test. And of course, as you can see, we loaded now the reconfiguration module 1 with F1. Look, even for the same inputs, right, we are getting now different outputs, EE, D2, DD7, and the last one E3, FF, D, DEF. There you go. Okay. Now what else? Now after that, if you remember, we reconfigure once more, right? We reconfigure it back to the second reconfigurable module. So for the same inputs, right, we're getting these values, which are different, of course. C1758DDF, and then at the level is 9FF8, C8DC2. Okay, so you see, this simple project shows you, how you can implement a hardware-software project that has a reconfigurable component, no, actually a runtime reconfigurable component. Here, as you can see here, the software took care of reconfigure the hardware itself. Okay, this is what we call a self-reconfigurable system. Okay, well, thank you so much.